Okay, so before we start the volume investigation, let's just have a quick review of how to draw a three-dimensional shape. The easiest way to draw a three-dimensional shape that I have found is to draw the face. So you'll see there's a face here. And if you just drag that over for a second, so say you start with that face. If you reproduce that face again, but just slightly back and to the left, or to the right, my apologies, and then just join the corners. So you can do something like this. You can get a bit of, or a very close drawing to the three-dimensional shape that I've drawn here. Now I've done something else with the black diagram here, as I've used dotted lines to show hidden lines. That's one of the ways we create the illusion of depth. This starts to get, oops, I missed one. This starts to get a bit messy if you leave them all as solid lines. It's a little tough to do with the marker, but that's one way to draw a three-dimensional shape. And you can do that with a whole bunch of things. So we have prisms here and pyramids and a bunch of things. So if I take this face plate of this rectangular prism, if I draw it a second time, and I'll just slide that back, I'm going to take advantage of that shape. If I just slide it to the back, and then I connect the corners, okay, and then maybe I'll put this one as dashed because it's a hidden line, I can draw my three-dimensional shape pretty quickly. For a square-based pyramid, so I would have to find this center. Now, because we're working in 3 dimensions, this piece that's on the ground here is a square, but it's a square laid flat on the ground, so we're getting the illusion of depth. Okay, so if you picked it up, it would be a square. Okay, as you let it fall closer to the ground, you can try this with a piece of paper. You could see how it looks, or the appearance changes. Okay, so this is a square on the ground. If I extend to some pinnacle or some point, and then I just connect the corners, and I might connect with a hidden line back here, that's how I can draw a pyramid. So just a few tips on how to draw three-dimensional shapes. You might find it very helpful for this section. So we're going to do volume of three-dimensional shapes. Okay, so a prism, and this is a key word to know, prism. A prism's not a pyramid. Okay, it's something different. This is a prism, is a 3D figure with 2 parallel, congruent, polygonal bases. Oh my goodness, that's wordy. Okay, so we have things like rectangular prism and triangular prism. So an easier way to think about it is a prism has the same cross-sectional shape along its entire length. And you've seen this all the time, a Rubik's Cube, a shoebox, a soup can, even the toothpaste that comes out of the tube when you squeeze it. Okay, has the same cross-sectional area. So cross-sectional area just looks like this. Okay, so if you looked at this shape right here, and you were to drag it down throughout the length of the object, you would see it maintains that shape, that area, throughout its width. It doesn't flare out, it doesn't get narrower. Okay, that's maintaining the same cross-sectional shape. So when I say the area of the cross-section, that's what I mean. Okay, so let's do a couple here. The volume of any prism is given by the following. So a rectangular prism, so the rectangular part right here tells us what that cross-sectional area is. Okay, so any prism, the volume can be found by taking the cross-sectional area and timesing it by the length. Well, this is a rectangular prism, so if we looked at the area of the cross-section, in this case, it would be W times L. Okay, so if we put that in here, W times L is the area, okay, times the length. Oops, I should have used a different one here. Doesn't really matter. In this case, the length for this question would be h, or the height. So let's just have a quick review here. This is the area. This value here, okay, is the depth or the height of the object. You can't fall in love with the letters. Okay, you just have to sort of understand the pieces we're talking about. So we have an area times its depth, its height, its length, however long that shape is, that's the other dimension. Okay, so don't fall in love with the letters. Sometimes they're going to conflict. You'll have H's in the wrong places and L's. You got to keep in mind what we're looking for here. So the volume of a rectangular prism, okay, is just length times width times height. If you looked at this question, we could even have this could be our cross-sectional area, and then this could be our depth or the length of the shape. So there's lots of flexibility here. Okay, so let's take a look at a triangular prism. So we have a cross-sectional area here. It's all shaded in blue. So the area of a triangle is 1/2 base times height. Okay, and there's the height, there's the base, and then times the length in this case, so it's the L matches up nicely. Okay, and that's how long or how deep that shape is. So to get the volume, we would just multiply those values together. You're probably seeing a trend here. The volume of a prism is given by the following for a circular prism. Now, a circular prism has the fancy name of cylinder, and again, it's the cross-sectional area times the length times the height times whatever the depth of the object, that dimension. So the cross-sectional area for this one is pi r squared. That's the circle. And then the length of this object, the height, the depth, in this particular shape, it's an h. Okay, so that would be the volume. Now I have a reason for showing you all of this, and I'll give it to you in 2 slides. Okay, the volume of a right pyramid, now this is a different word here, pyramid. Pyramid is not a prism. Okay, so a pyramid is a different shape. So we're looking at right pyramids. Those are ones that just go straight up and down. There's not skewed to one side or the other. And what we find is that the volume of a pyramid is 1/3 of the exact same shaped prism. So let's see if I pick this up. Let's see if my image will move. If I pick this up, you can see how it fits inside. Okay, well that volume of that pyramid is 1/3 of this prism. So if this one here has a volume of 1, this has a volume of 1/3 of that. So again, we'll just take the cross-sectional area of the base, whatever it might be. It'll be 1/3, let's say width times length, and then we'd have to give it some sort of third dimension or height. And this would be the cross-sectional area. Okay, again, don't fall in love with the letters, they're just dimensions. Keep the big ideas in mind. If we look at something like a cone is very similar to a pyramid, only instead of being matched up with a prism or a square-based prism, it's matched up with a cylinder. Okay, so we would put cross-sectional area in here, would be pi r squared. Okay, and the length in this case, the depth of this, we would be using an h, and we would have our 1/3 out front, and that would be the volume of a cone. Now, the good news is you do not have to memorize any of this. So what we've just gone through are these shapes right here. So we have all of these shapes. You will always have these formulas provided. No one ever asks you to memorize these, but you can print this page off. It's also on the website as a formula sheet. It's right off the EQAO website. But what you should be familiar with is, can you read the name, can you find the letters, and where they fit in the formula? That's really the important piece you want to look at. So if you found you were working with a cylinder, you should be able to identify the radius, the height, and where they go in the expression. Okay, and you'll notice for all of the ones that are prisms, okay, so cylinder, rectangular prism, triangular prism, they all start with the area of the base times the height, or times the length, or that long dimension is what they're looking at. Okay, so take a little bit of time, just look at those formulas, get familiar with where the numbers go in the formulas. Again, you'll never be asked to memorize these. Okay, so let's actually try a question. Find the volume of a can of soup that has a diameter of 12 centimeters and a height of 22 centimeters. Okay, well, cans of soup are generally cylinders. Okay, so I would draw my cylinder something like that. I have a height of 22 centimeters, and I have a diameter, that's important to note, of 12 centimeters. So if I looked on my formula sheet, or if I could remember, this is just a cylinder, so if I find the area of that cross section and I times it by the length or the height in this case, then I can come up with the volume of this shape. So the area of that cross section, that shaded piece, is pi r squared. So, but for us, this is my diameter, so my radius must be 6 centimeters, 6 squared. So there is the cross-sectional area. The height of this can is 22 centimeters. Okay, and once we have all of the information in place, it just becomes a matter of being a calculator question. Okay, so pi is 3.14 times 6 squared times 22, and I get, oh boy, 2,486 cubic centimeters. Okay, let me just double check that. So 3.14 times 36 times 22. 1, 2, 3 looks about right. And you'll notice, please pick this up right here, because this is a volume and we're multiplying 3 dimensions together, it has a cube on it. That means we're looking at how many little cubes fit inside this can. Okay, so 2,486 of these little cubes would fit inside. Okay, a cardboard box has a volume of 8 cubic feet. Okay, so we don't work with feet too often, that's okay. What might the dimensions of the box be? Include a diagram. So a cardboard box could be something like that. It doesn't tell me that it's square based, it just tells me it's a box, and I know that boxes look something like that. Okay, so now I get to choose. It just says it has a volume of 8 cubic feet. So options could be something like whatever 3 numbers. Okay, so if this is a prism, length times width times height. I have to have 3 numbers here for these dimensions that multiply for 8. So one possibility, we could go with 1 foot, 1 foot, 8 feet. So that would be 1 times 1 times 8, and that would get me 8 cubic feet. I could also, and I'm not going to change the diagram, I could also do something like this. I could make it a cube or a box that has all same dimensions in all directions. I could do something like this. 2 times 2 times 2, that's another way of having 8 cubic feet. So there's many answers you could do. Those are probably the 2 easiest to find. It's just getting comfortable that you have to have 3 dimensions multiplied together to get to this piece. Okay, so thanks for tuning in. Here's a couple questions to try on volume, and thank you again.